Welcome, class. So today we are going to pick up talking about Chapter 7, Thermochemistry. So thermochemistry is the relationship between chemistry and energy. So in this chapter, we're going to focus on some of the basic concepts of how energy interrelates with the physical and chemical changes that we've talked about in the chapter so far. So thermochemistry is a part of, or a subset, if you will, of the field of thermodynamics, right? And later on in Chem 2, we'll do a more extensive look at thermodynamic concepts. But for this chapter, we're just going to focus on some of the basic ideas of energy and energy transfer and how we really think about it when we think about physical and chemical changes. So thermodynamics as a whole is the study of energy and its interconversions. And thermochemistry looks at specifically sort of those applications between chemical and physical changes. Now, one of the big underpinnings, right, of thermodynamics is the first law of thermodynamics. Now, you probably know this better as conservation of energy. Which essentially says that energy cannot be created or destroyed. When a change occurs. So, while it cannot be created or destroyed, what we'll look at or see is that energy can be changed, if you will. It can be changed from one form of energy to another, and it can be moved from one place to another. Now, if we think about energy as a whole, a very simple way that we can sort of define energy is the capacity to do work. Now, energy can be broken up into two components. It is work and heat. Okay. So before we get into work and heat, let's look at the types of energies that we can have. So if we break down energy into two big sort of pools, we have kinetic forms of energy, and these are forms of energy that have to do with the motion of something. Now, in chemistry, the most important type of kinetic energy that we look at is thermal energy, right? And this is the energy associated with temperature. Now, the way that we usually think about this in terms of the kinetic aspect, it's associated with the motion of atoms and molecules. So previously, right, we've talked about that the atoms and or molecules of some sort of matter are in constant motion. That motion, right, is a measure of its thermokinetic energy. And remember, as temperature changes, right, how fast that motion is occurring changes, right? Higher temperature, we have faster moving atoms and molecules, we have higher thermokinetic energy. Okay? And on the other hand, we have potential forms of energy. And you're all familiar with potential energy, probably most importantly with gravitational potential energy that you've learned about in physical science classes. But in chemistry, we're going to look at chemical potential energy, right? And this is energy associated with position or composition, right? These are what potential energies are. And so specifically chemical energy is that energy associated with the position and type of electrons and nuclei, or atoms, if you will. So to sort of get down to what it comes, so this is the energy associated with the composition of matter. So we have a particular molecule, it's made of a particular atoms in a particular arrangement, in a particular way of bonding, right? And all of those things contribute to how much chemical potential energy a particular molecule has. So we have kinetic energy, we have potential energy. And so this energy, right, can be subdivided into work and heat. Now, work is a force acting over a distance. So we might think about this as pushing something across the floor, right? We're applying a force to move something over a distance, or inflating a balloon, right? Where we're applying a force to move that balloon in terms of inflating it. Now, heat is the flow of energy caused by a difference in temperature. And heat will be the most important thing that we look at here. Right? In chemistry, we try to set up our systems to where we don't really have to worry so much about work, but we focus on the heat aspect. So that's going to be our prime focus as we move through this chapter. Now, we have to talk about energy units. So there's two primary energy units, the calorie and the joule. And you can see the conversion factor here that 1 calorie is equal to 4.184 joules. Now, joules are the SI unit of energy, right? So this is the SI unit, so this is sort of the official unit. And a joule is defined as the amount of energy it takes to move 1 kilogram 1 meter. Okay. So it's how much energy it would take to move 1 kilogram by 1 meter. Now, if you think about, if we sometimes look at the units here and break them down a little bit, a joule is defined as 1 Newton meter. So remember from physics, a Newton is a unit of force, a meter is of course a unit of distance. Now, a Newton is equal to a kilogram meter per second squared. So mass times acceleration, right? So we have a kilogram meters per second. So if we combine these, a joule is equal to a kilogram times meter squared over second squared. Now, if we think back to our old kinetic energy equation that we've seen throughout the course, we have, right, 1/2 mv squared. So in other words, a mass times a velocity squared. So kilograms times meters per second squared, right? So this is our classic unit of energy in chemistry, is the joule. Now, the calorie is also commonly used. It is an older unit of energy, and a calorie is equal to the energy needed to raise the temperature of 1 gram by 1 degree Celsius. And so these are our basic units. Now you will come across a couple of other units. Should note that there is a big C calorie, sometimes called a food calorie, that is actually just simply equal to a kilocalorie. So in other words, it's 1,000 normal calories, and they've just come up with a different way to express that when we deal with food. So when we think about food, when you see packaging, it's really kilocalories that are on the label, even though we call it a calorie, but it's a big C calorie. So, but this units conversion is one that we want to be able to work with. Now, kilowatt hours, we're not really going to focus on. It's an electrical unit, just an example of another unit of energy. Okay, to summarize so far, we have potential forms of energy, we have kinetic forms of energy, and we have this idea of conservation of energy. So let's turn our attention to this idea of conservation of energy. So remember, this means that the energy is constant. Now, in a bigger sense, right, we can think about that as, right, we can't create energy when we do a chemical or physical change, but in sort of a bigger sense, it means the energy of the universe is constant, right? So if energy is a big pool, right, we have a certain amount of energy out there, it doesn't change, right? It may move around, it may switch from one form to another, but the overall pool of energy is the same. So the way that we've decided to look at chemical and physical changes is that we're going to look at dividing the universe into two parts. We're going to have our system and our surroundings. So the system, right, is the process that we're studying. So this is the physical or the chemical change specifically that we're looking in. Now, something to keep in mind is this is very narrow in its definition, right? So when we talk about the system, we are typically talking about just the chemicals, the molecules that are interacting, just the atoms and molecules that are changing, right? And almost nothing else. So this will become important as we get into different aspects of this. And the surroundings is everything else. Now, we tend to, in our focus, eliminate or make the surroundings sort of the immediate surroundings, right? Because the energy is not going to travel, huge distances, right? So, but it's essentially everything else besides the system. Now, a couple of things to keep in mind as we move forward here is that, so we talked about that it's a zero-sum game, right? So the energy in must equal the energy out. So if I have the energy of the universe change, its change is zero. So that means if there's a change in the system, that means there also must be a corresponding change in the surroundings. And those changes must add up to zero, right? So in other words, if the energy of the system goes up, the energy of the surroundings must go down, right? So if we think about this change over here, and if we had the system at, say, half full, and the surroundings at a quarter full, and we had a quarter of the energy flow out of the system, so it drops, that means the surrounding must have gone up. And so, while the energy has changed places, the total sum, right, a half plus a quarter, is the same in both situations. So, the net change here, again, is zero. So the energy of the universe didn't change at all. It just moved from, in this case, our system that we're studying into the surroundings. So this is how we're going to focus when we look at things. Now, the other aspect that I want you to think about, and this is a more general thing to think about as you go through these different scenarios that we'll talk about, is that systems will tend to move toward lower potential energy. So it's one of these sort of basic universal concepts that systems at high potential energy will tend to move toward lower potential energy. So if you have molecules that have a lot of chemical potential energy, think about fuels, they will tend to react easily to release that energy, right? To burn, right? Or to release that energy so that the system moves to matter or to molecules that have a lower chemical potential energy. Okay. Now, some other relationships that'll become useful here is that we will often talk about the system as the reaction. And if we think about the energy change of the reaction, it's going to be equivalent to the energy in our products minus the energy in our reactants. So this is sort of like saying the change in energy is equal to the final energy minus the initial energy, right? So a lot of times, one way we're going to look at this is look at, okay, what are the energy of the products? What are the energy of the reactants? This will define my change in energy, or the change in energy of the system has undergone. Now, that system or reaction, again, has to be equal to the opposite change of the surroundings. So another relationship that we want to remember is that whatever the change of the system or the surroundings, the other one is simply equal to the same magnitude but the opposite change, meaning gain or loss, right? So if one side gains, the other one has to lose exactly the same amount. So, for example, if we were to take carbon and oxygen and react them to make CO2, what we see is the energy of the products has a certain value, right? It's low. The energy of the reactants is higher. If we take the product minus the reactants, we're going to get a negative number, right? And this simply indicates that over the course of this reaction, energy was lost or released into the surroundings. So these are the ideas that we're going to be looking at as we go through this chapter, and we're going to be looking at various aspects of it.